Hello, welcome back. Today we're going to take a look at spherical coordinate systems and how we can use triple integrals to find their volume. Today is really going to be useful for us, especially if we are talking about spheres or cones. We'll see those in just a few moments. So we've had a few formulas from earlier this year where we learned how to convert rectangular to spherical. And the equations are here. We could say that x was equal to rho sine phi cosine theta, y was rho sine phi sine theta, and z was rho cosine phi. And the other way around, we got x squared plus y squared plus z squared equals rho squared. And this is the equation of a sphere for us. Down below we have our a representation of how we can do those conversions. And what we wind up with, though, is we wind up with a wedge. Like if I were to take this little line right here, and if I were to, like, let's say, spin it around, like going like this, going up and down, notice we're going to get kind of like an arc length at the very top. But if we spin that around the z, we get this spherical wedge looking like this, looking like an ice cream cone. But let's talk about the restrictions of these. Rho, remember, is a change in our radius. So the radius typically starts at the pole, which is going to be 0 for us, or from A to B depending. Phi is the angle measured from the positive z-axis. Now this typically has a domain 0 to pi, you might remember that. And then we have theta, which is like our polar one, just like the polars on the xy plane, and this goes from 0 to 2 pi. If you had questions on how we got these, take a look at one of my most amazing videos from earlier this year. So here's an example of the spherical wedge right here. So what we're trying to do is we want to find the volume of the wedge. Now I'm going to leave the proof here for later on in another video. Don't have enough time for this video, but we will do another video on that shortly to come up with the volume, a proof for the wedge. Now notice the volume of the solid is just the intersection of a sphere and a cone. So that's kind of like what we have when we talk about if I were to rotate this up here, going up, come on, there we go, right up here, and if I were to revolve that, of course we would have this top part for the radius, we would get like an ice cream cone right here. To calculate the volume, here's what we're going to do. We're going to take our rho, so if I pick a point on top of here, and if I were to extend the line from the pole out here, of course, this length right here would be rho, that's our radius. If I project this line onto the xy plane, we get something like this. This is the projection of our line on the xy plane, right there. And we're going to rotate this line right here, our rho, our radius, around the xy plane. And that's what's going to give us a change in theta. Now next, we're also going to take this line and we are going to move it up and down with the z-axis. We're going to rotate along the z-axis too. So we've got 3 planes of rotation. So we got this right here. We're going to rotate around the z-axis, and then we're going to move it up and down, angle it from the z-axis also, and that's going to give us phi right there. So to get the volume, we have this little formula right here. Now we've talked about this. For rectangular coordinates, to get volume, it was dz, dy, dx. For our cylindrical, sorry, about to say polar, cylindrical, I think I just spelled that wrong. We said it was r dz, dr, d theta. And for polar, our base formula, just right here, is going to be the following. Rho squared sine phi. Now again, I'm not going to prove this in this video, but we'll take a look at another video where we have a proof of this. Rho squared sine phi d rho d theta d phi. So this finds volume. Now we can switch these around, which you will probably see me do more in this video. I tend to do d phi before d theta, and it's okay. So this is the equation right here to get our volume of our sphere. Now it looks pretty nasty. It does look pretty nasty right here. But you want to take a look. there's our rho squared sine phi, our d rho, d theta, d phi right there. But all this right here, this is just like my x coordinate, this is my y coordinate, and this is our z coordinate. These look really bad, but most of these turn out to be constants in our limit. So let's take a look at one example here real fast together. Let's see here. So suppose we're asked to find the volume of a sphere with radius 4. How would we set this up? Using a triple integral to calculate the volume. We know how to find volume of a sphere, 4/3 pi r cubed, but let's see if we can use our triple integral to do this. Since we are using a sphere, it should make sense that we're going to use spherical coordinates. Here's how we can find the limits. First, we need to determine the change in radius. That's our change in rho. So we need to find our change in rho. Well, what's the smallest rho going to be? Well, if I'm making a sphere starting from the center, if I want to make a sphere, right, starting from the center outwards, my smallest radius is going to be 0. My largest radius will be when it hits the outer sphere itself, which is 4. Next, we need to determine the change in the angle it makes with the z-axis. That's our change in phi. So my change in phi, well, the smallest from the positive z-axis, let's see here, we're measuring all the way down, even to the negative z. So there's my positive z. We're going to measure all the way down to the negative z. Well, we start here at 0 degrees, or radians, and all the way down here is pi radians. Remember, phi only goes from 0 to pi, maximum anyway, so that's because we want one complete circle there, half circle there. All right, now, next we need to change to determine the change in the angle in the xy plane. So now, on the xy plane, we're going to spin our little arc here around the xy axis. So that's our change in theta. Well, our change in theta would be just 0 to 2 pi, since we're going to go all the way around. Now, we can write our integral. Don't forget your change in volume formula, though, okay? Don't forget the dV. This right here is the volume of our spherical wedge as it's moving around our xy plane, or as we're moving it around. So this is the volume of our spherical wedge. So it's kind of confusing. Remember our little wedge right here. The volume of this wedge is going around, all the way around. Phi goes from 0 to pi, theta goes from 0 to 2 pi, and phi goes from 0 to 4. So we're going to write this out. So our change in volume, it's my formula, spread it out. My formula here, remember, is rho squared sine phi. You have to include that every time. This is like that r in our cylindrical coordinate, r dz dr d theta, right? And then we're going to have this d rho, d phi, d theta. Like I said, I tend to switch those around, old habits. D rho, well, that was from 0 to 4. D phi is 0 to pi. And d theta, 0 to 2 pi. And you can integrate this. Ready? But we're going to go and type this in our calculator. It's always good to practice typing these in your calculator. Press enter. Menu 4-3. The first one goes from 0 to 2 pi. Menu 4-3. 0 to pi. Menu 4-3. 0 to 4. Now be careful of your variables. There is no rho variable, so I'm gonna let rho be x, y, z. It's okay, the calculator doesn't read that. It just reads it as a letter, so I'll go x squared, now you gotta be careful, times sine, now be careful, we gotta be really careful here. I am going to let rho be y. Sorry, that's phi. Let phi be y, sine y. So you gotta be really careful. So over here, I already let rho be x, so dx. Because I let phi be y, I'm going to use this as y and z. If you calculate the CAS and the CX do have Greek letters, but it's just easier just to type these in because it's quicker and more accessible. And I press enter, and notice we get 256 pi over 3. So we go 256 pi over 3. And just for reference, let's find out what the actual volume is. 4/3, whoops, that's what we're looking for, 4/3, control divide, ready? Control divide, 4/3 times pi times the radius cubed, so it'll be 4/3. And again, we do get the same answer. So this formula does work for us, and that's really nice. Alright, so going to number 2, we'll take a look at a few more examples.